Okay, so no need to write this down. You guys had this from the very beginning of the chapter. One of the characteristics of a liquid is that it has the ability to vaporize. Right? So we've been talking about the way that happens, right? That you've got liquid molecules that have IFs between them, and they have to gain enough heat that they can overcome those IFs and turn into a gas. Right? Evaporation is when it happens exclusively on the surface, and boiling is when it happens all throughout the liquid. But if you read the boiling definition, it includes this stuff about vapor pressure, right? That the vapor pressure of the liquid is the same as the pressure, P, of the atmosphere. So that's what I wanted to dive into. Like, why is pressure a factor with boiling? So if we looked at a substance that wants to boil, unlike the other phase changes, the molecules not only have to separate from each other, meaning overcome the IFs, they also have to escape the container, right? Because that's what gas particles do. Gases should be able to expand and spread out and stay in continuous motion. All right, so the first thing that you have to overcome are the IFs that are linking it together. So I'm going to draw that in the red. Say I have 2 or 3 water molecules down here. Right. Those 2 or 3 particles have intermolecular forces holding them together. All right, so depending on how strong those forces are, you would need a higher number value to boil it, which is why every substance doesn't boil at the same temperature. Right? So if we're looking at factors that affect our boiling, and I'll say that's factors that keep liquids together. We've just listed one of them. First one are your intermolecular forces. All right, so we got to get some heat to this container, and the heat can speed up those molecules and allows us to break some of these IFs. Like, now you've got this red particle that's a gas, and because gases are less dense than liquids, it rises, but it has to fight its way through the surface of the liquid. And don't forget, you have particles out here in the air that we call atmospheric pressure that are colliding with the surface of the liquid. So this molecule that I'm about to color in the blue, it has to break away from the other liquid ones, and it has to be able to fight through that atmospheric pressure to exit. Right? So the second factor that these things have to overcome is the pressure of the atmosphere. So the reason you're seeing pressure listed in the definition of boiling is this blue particle's pressure as a gas, its vapor pressure, has to be as strong as the atmospheric pressure. Otherwise, it can't escape the surface. All right. And every molecule would have to possess that amount of energy for it to leave and boil. All right. So you got to overcome the intermolecular forces that hold that thing down, and you have to overcome the atmospheric pressure. All right. So before all this stuff went down that we were working from home, we did scenarios with gas laws, and we talked about training at altitude, right? Or why athletes will wear those masks, and it had to do with manipulating pressure. The same is true for boiling. So I want to walk you through one of those, and then talk to you about how your like neti pots and your pressure cookers at home work. So in your notes, I would just call this a scenario. And let's label it cooking at altitude. All right, so just like we did in class that day, we pick two locations, one that we know to be pretty high up, and one that we know to be close to sea level. And very often we get Denver, the Mile High City, and I get New Orleans. All right, so imagine we have two pots, and let's make it be water to start. We're boiling noodles. Here's my New Orleans pot. Here's my Denver pot. All right. If both of those substances are water, the IFs in those locations will be the same, right? Because the structure of the molecule dictates the IFs. So both pots have water in them. There's no IF difference between my two pots of water. But there is a pressure difference in those. In New Orleans, I have atmosphere pushing down. And in Denver, I have atmosphere pushing down as well. But those atmospheric pressures are not the same. You guys told me that when we are at altitude, that the air is thin. There are less particles in the air pushing down. So at Denver, we have low PATM. And in New Orleans, the air is much thicker. We have high. Atmospheric pressure. So what happens is my water molecules in Denver are able to break their IFs and fight through the atmospheric pressure with relative ease by comparison to my water molecules down here, because there's less atmospheric pressure to overcome. And you notice it in their boiling points. A pot of water, right, in Denver, right, will boil around 95 degrees Celsius. And in New Orleans, it tends to be at what we would accustom the boiling point of water, 100 degrees Celsius or 212 Fahrenheit. Right? So as we start lifting pressure off the surface of the liquid, it doesn't take as much heat for it to boil. Now, the crazy thing is, though, they're both boiling, but they are not the same heat. Right? So everyone thinks, oh, in Denver, things will cook faster. Right? In Denver, actually, things will cook slower because the boiling pot of water isn't as hot as it is in New Orleans, right? Visually, they'll both be like bubbling in the visual end that you know is boiling, but that pot doesn't have as much heat, and it's heat that cooks the noodles. All right, so usually I sum some things up that I want you guys to write down next to these. I'll just type them out for you. All right, so jump down here. We would conclude liquids must overcome T external and IFs to boil. Conclusion 1. Conclusion 2. At higher altitude, the external is less, so the liquid doesn't need as much energy to escape. And by energy, I mean it will happen at a lower temp. Therefore, less temp is needed to boil the liquid at altitude, but it takes longer to cook because the water possesses less heat. All right, so those are our big conclusions that relate boiling, the visual effect that you guys know as boiling, and cooking, which are two different things. Cooking is about heat. Boiling is about getting liquid molecules to turn into a gas and be able to escape the container, which involves pressure as well. All right, so one of the newer things that you're seeing are these pressure pots that they use for cooking. And the cool thing about those is it doesn't just have to be a liquid, it can be a solid. So I kind of wanted to bring up a picture of one of those and talk you through how that works. All right, so if we look at this guy here, copy it. And paste this thing in here. All right, just gonna show you how this works because it works on the same fundamentals. Right now, if you don't have one, right, one thing you're gonna find is even though you're cooking solids, whether it be meats or rice is a really popular one, you can make sausage in it. You can pretty much cook anything. You have to put some water into it no matter what you're cooking. So you put some water in the container at the bottom. Right. And then you put all your other stuff, right? So I'm going to try to like label up your picture. Here's your solids, right? Sitting there, you've got some rice, you've got some carrots, right? That's what's going on. Right. Then what happens is you put the lid on it and it seals it, right? And some of them you put on your stovetop and some of them have their own heating element, right? But the moral of the story is they start heating up the water in here until the point that the water vaporizes. Right? But why this works is the water is sealed. So it starts bouncing around in here because it can't escape. So it starts raising the pressure inside of the pressure cooker. And as the pressure above the water goes up, there's more forces pushing down on the liquid, making the next water molecule have to get hotter to escape. And then there's more forces pushing down. So the water gets hotter and hotter and hotter, and it elevates the boiling point of the water inside of there. And it elevates the boiling point of the steam. The steam is getting hotter as well. So a normal boiling point for water would be 212 Fahrenheit. Inside your pressure cooker, you can see up here, that's happening at like 250. So there's a lot more heat in the pressure cooker because of the pressure needed to make the water vaporize. Now you've got all this steam that's super hot, and that steam can't go anywhere. So that steam comes down and it comes into contact with the surface of the solid, right, and the liquids. And now your chicken and now your ribs or your rice or whatever's in there, right, is experiencing more heat than it would if the pot were open. And because it's experiencing more heat, it cooks faster. It cuts down your cooking time. And this one here even showed you that. Like whole chicken usually takes an hour to cook. It'll do it in 15 minutes because there's so much more heat energy present because of the higher pressure. Brown rice boils in like 20 minutes. Like black beans can boil in 15. So these are really cool. They can save you a lot of time in cooking. And there's not a lot of prep. You just mix it all up in there, close the top, lock it so that the pressure builds up. All right. And then what happens is there's a bunch of different valves on it, right? And you open those valves one by one, and it gradually decreases the pressure so that you're not releasing super hot steam all over your kitchen. And then as the pressure goes down, the lid becomes removable, and then there is your cooked food. All right. So a pressure cooker makes the pressure in the container higher, which makes the temperature inside of there higher, which possesses more heat and cooks the food fast. All right, and that's how your pressure cookers work. All right. Questions from any of you guys about the boiling process or the whole idea of like pressure factoring in, anything like that? All right, so stop recording.